Hi, I am Robin Magnet, and I am going to present our paper Memory-Scalable and Simplified Functional Map Learning, which is a joint work with Ovsjanikov. In this work, we present a novel functional map learning pipeline for unsupervised 3D shape correspondence. Without decreasing performance, we remove the requirement of standard pipelines to differentiate through a linear system, which can be unstable in some cases. Finally, we provide a memory-efficient implementation of dense correspondence matrices, which enables us both to process very dense meshes and to compute several of these matrices in parallel. The goal of 3D shape correspondence is to find corresponding points between 3D shapes, as shown on the example here, where we seek a map T, which, for every point X on shape M, provides its corresponding point Y on shape N. State-of-the-art methods in unsupervised correspondence learning usually rely on functional maps, which can here simply be seen as a low-dimensional embedding of the correspondences as a small k by k matrix. The standard pipeline for unsupervised functional map learning usually takes two shapes as input and feeds them in parallel to a feature extractor, usually diffusion net. Diffusion net, or any other feature extractor, outputs high-dimensional features for each vertex on each shape, and each feature can also be seen as a function on the shape. Eventually, using some linear system solver, a small functional map can be obtained, on which the losses are applied to enable training. More modern functional map learning pipelines have noted that it was helpful to compute another functional map on a second branch. This second branch uses a similarity matrix pi between all vertices, which is usually obtained as a simple transformation of the distance matrix between the vertices. This matrix pi is called a dense correspondence matrix and can be embedded into a new functional map, C tilde. Using the same losses as before, only a loss enforcing the similarity between the two functional maps is added. This pipeline has, however, two major drawbacks. First, it requires differentiating through a linear system, which is known to be an unstable operation. Second, the dense correspondence matrix is a dense matrix, whose size scales quadratically with the number of vertices. This requires a significant amount of GPU memory to process very dense shapes. In our work, we therefore present a novel single-branch pipeline without linear system solver. Our method computes a dense pointwise map pi and feeds it into a popular map refinement algorithm called zoomout, which we both ported to GPU and made differentiable. This outputs a refined functional map, which we use to guide the initial correspondences we obtain from the features. While this removes the linear system solver, there are no multiple dense correspondence matrices to store for each forward pass, as zoomout requires multiple conversions between functional map and pointwise maps. To handle this, we propose a scalable implementation of these maps. This relies on the observation that such dense matrices are only used inside matrix products, and that they are also usually derived from a simple distance matrix. Therefore, we take advantage of the matrix product and notice it can be computed blockwise on the GPU without ever storing the entire matrix in memory. Eventually, this allows us to process very dense meshes with both a low memory cost and good performance, as seen on the texture transfer example.